Hello everyone. Today in this lecture, we'll see how to write the verilog code for NVIDIA and also self-checking test events. Also, we'll see how to synthesize the code by using Leonardo Spectrum. So to design that NVIDIA adder, we'll require the half adder and full adder. So first we'll design full adder. So for that, I've opened the models. From that, select File, New, Source, Verilog. So here start writing the code for the full array. Full array. ABC sum ABC cout and sum that we need to specify which are inputs and which are outputs. Input A comma B comma C, output sum comma cout. Now we need to write the functionality of the full array. That means it will add the three numbers, 3 digits, C plus B plus C. So for that, we need to write this sum expression and cout expression by using the procedural assignment statement. Assign sum equal to A XOR B XOR C. That is an XOR symbol, logical symbol. Next, carry out, assign, cout, AB, BC, CA, content R operation, and or logical or symbol, logical and so this is the expression for carry AB plus BC plus CA. And with this, we completed the functionality of the full adder. So end this module by writing the end module. So one module completed to design the full adder, like here we are designing the n bit. N bit adder. So that here n bit means A of n minus 1 down to 0, B of n minus 1 down to 0. So here the first I may use the half adder, one half adder. So for that we need to apply first of all E of 0 and B of 0. So it will generate the sum 1 S of 0. And the next carry bit, the generated carry out from the half adder will be act as an input carry for the next stage full adder. And here A of 0, A of 1, B of 1. Like that it will follow, it will generate the next sum bit S of 1 and next full adder and so on up to nth full adder. So like this, we'll design the n-bit full adder. After that, we will verify it by using the self-checking or normal test bench, by writing the normal test bench. So the size of the output I may consider as an yes and down to 0. Why? Because I'm including the cout also inside this particular sum output. Because of whenever you add 4 bits, that will generate the 5-bit answer. So we'll require n plus 1 size of the output. So now write the code for the half adder. Just copying this one, pasting the same place. Half adder. Only two inputs for that. So I'm reducing the expression for half adder are A XOR B and A and B. So I'm deleting the remaining. So with this, the required modules are completed. Now we need to write the code for the entire A and B adder. So for that, I'm starting with the module and bit adder. The inputs A, comma B, and output is a yes. In module, specify which are inputs and which are outputs. If you want to write this is an n-bit adder, means we need to. I'm writing the parameter form, parameterized circuit parameter. I'm defining it as an n equal to 8 bits. So here the inputs n minus 1 down to 0, A comma B, output n down to 0. Yes. So I'm declaring the intermediate lines by final output carry underscore out and intermediate carries. That is when we require n minus 1 number of n minus 1 down to 0 number of carries. Carry. And next. Here I'm using the generic statement in order to generalize the n-bit adder. So for that we require the extra wiring connection, that is n minus 1 down to 0 S1, then some outputs from the intermediate full adders. So now from here the code will start generate. For that we need to declare some variable like generate I. Generate. Now write the generate statement. Generate for I equal to 0, I less than n, I equal to I plus 1. That means that will start from I equal to 0 and increment it by 1, and it will the loop comes out when this condition will false. And next I plus 1. We need to begin the loop. We need to write the name of the loop. I am writing the adder only. Adder. Now for the first case, we are applying A of 0 and B of 0. For that, I'm writing some simple case I double equal to 0. When I double equal to 0, we'll use the half adder. I'm writing the function name as an instantiation name as an UUT. Then I will write A of 0 comma B of 0 carry of 0 and S1 of 0. So next condition else otherwise we'll move to the full adder UUT1. Don't give the same names, same instantiation names UUT. You give the other names. So here BR5 comma BR5 carry of I minus 1 comma S1 of I. S1 of I and end this loop. And now assign the final carry out, final carry to the carry out signal, carry out. The last carry is a carry of n minus 1, carry of n minus 1, and end this generate loop using n generate statement and generate. Now assign the final output to the S, assign S equal to carry out comma S1. So like this we can write the code for the ladder n module. So here I'm writing a simple test bench only, not writing the self-checking test bench. So module and with ladder tb n module parameter capital N equal to 8 I'm giving. So next need to call the function here. Need to call the module with estimates, which we are going to verify the functionality. So here part of this is an instantiation of that one parameter. Otherwise, we can simply write 8 also. Next, we need to give the instantiation name. Here we can give the same UUT. Why? Because this is a different code from that one. So we can use the same UUT as a name here. So in that we need to declare rich inputs as the inputs in the form of rich n minus 1 down to 0, a comma b, and outputs declared with the wire n minus 1 down to 0 and yes. So with this, the instantiation and inputs are input and outputs are declared. Now we need to give the some inputs to the circuit in order to verify the functionality. For that, we need to use the initial statement. Initial begin. I will give the capital A equal to 80, 45. Is an representation of number. D equal to 80, D 34, hash 100, A equal to 80, D 78, E equal to 80, 1, and end. So now we need to save this program. For that, file, save as. Wherever you want, we can save there. And with adder underscore, I'm giving the same name. All files save. Now we need to check the syntax errors whether the written code is correct or not. So for that, select compile. Now from this we need to select the location of your code where it is. Now here in this, we need to select your code and with TB compile done. Now we need to check whether there is an error. So here it is given some errors. Line 30, undefined variable S1. So I defined it in capital S. So here I have given small s, for that it has given error. The next 33 line. So here there is no semicolon. Need to put semicolon. 53 line. So just save the program and compile it. We'll check once again. So here I given the mistake, that is will be the D decimal number. Control is so I given double N. And that is also one error. See, now I hope get any errors now. So zero errors and zero ones. Now go to library, file, work folder we need to select. Then we need to select our nptel code. And nbit. For that we need to recompile the original model. Now select select the NB added module, test bench module. Now simulate. Select right click, add wave. run the code recently. Then n down to 0. So desimulate. Now run symbol. So select it all, Control A and right click, addings, and find decimal. 45 plus 34, 79, 78 plus 12, 90. Like that, we can write the NVIDIA added code also, like n equal to 64 or n equal to 128, like that. Like this, we need to verify the functionality. After this, we need to close this one. Before closing it, I'm copying this code to perform the synthesis. So for the synthesis, no need of test bench program. We need only the original code, like source code only. Now close the ModelSim. Now open the Leonardo Spectrum, which is used for the synthesis of a code and to analyze the synthesis program. So this is the Leonardo Spectrum window to perform the synthesis. So for that, select File, New. Otherwise, we can directly select the open files here. Open files, and then we can select the whatever the code we require. We can select that code here. Simply, I'm doing the same thing here. So I'm saving this program with the nbit added. File, save as, and nbit added. Extension is .b. Leonardo, I'm selecting the folder as an Leonardo folder. In that, I'm saving it. Save. And we added save. So now we need to. This is we need to set up the analysis part. For that here technology, we need to select the technology parameter that is in TSMC 180 nanometer technology 0.19 micrometer. So and then we need to select the file whichever we want to synthesize. That file we need to select. So here I'm selecting the nbit added file. So for that, wherever you save, we need to go there and we need to select that particular added function. Otherwise, whatever you want, that particular code we need to select and load it. And working directory we need to select. Here I'm selecting the working directory as in Leonardo. The same I'm selecting here, set. And next we need to select the constraint file that is in clock frequency you need to set. Here I am setting the 100 megahertz is in clock frequency. And next we need to define the netlist file that is an nbit added from synthesize from this Leonardo Spectrum. It will generate the netlist file. I will show how that netlist file convert the logical code converted into RTL like netlist. Netlist means that will convert into the logical gates. I will show that code after generating, after completion of the synthesis. Synthesis of our original code underscore 0. We need to write the other name of that particular module. Otherwise, the same code will remodify into the netlist. For that, the safe side, I'm giving the other name for this original file net nbit added underscore 0. Now simply click on run flow. So here I'm opening the command window. Listen command window. It will complete the process. Here this particular window shows the whatever the commands we use that will shown here. So I first set the driver working directly, D folder Leonardo 1, Leonardo Spectrum 1. So after that, I loaded the library TSMC 0.018, and then I read the verilog code. After that, I had given the clock frequency, and next I set the output file, and then I clicked on the run flow. So whatever the steps we follow, that will represent it here, that will automatically come here. And next we need to analyze how the RTL schematic is there and technology schematic and critical path, how to check the how to know the critical path here. So for that, so once again I'm running this one run flow second time. So this is the report generated from the Leonardo Spectrum. Now we need to see the RTL schematic. By clicking this symbol, we will give the RTL schematic. So this is generated the full adder, not the n-bit adder code. A, B, C, CA, PC, XOR, and then summer out. So if you want to see the technology schematic, click on this view technology schematic. And open the in terms of classical gates XNOR, like these are the standard cells. So next we need to see the critical path. By clicking this particular waveform symbol, we'll get the critical path. So this is a critical path. We'll start from the A input, A2, directly giving to the max to 1, like whatever the standard cells exist inside, it will come from A to the final C out. So we'll calculate the critical path starting from the input, and whatever the final output is there, from that we need to calculate the critical the path exists from the input to the final output. Like that, here also it performed. So whatever the path we got here, it will shown here. So data required time is in 10, and data arrival time is in 0.29. The slake path is this is a slake path means in the sense there is a difference between the required time and the arrival time. At what time the output will arrive at the output side, that is in 0.29, and slake time is 9.7. If this slake time is in negative, in the sense your constraint files does not met the requirement. If it is positive, it met the constraints. So like that we need to code the design. Now next we'll see the n-bit adder. So for that, n-bit adder and save. Minimize this window, open the command folder, and once again rerun the run flow. Now see it working for the n-bit adder. Now we'll see how many gates it's required to construct the n-bit adder. Like here n equal to 8. So n equal to 8, when we design the 1-bit full adder, it took only the 6 number of gates. Now here it has taken 46 number of gates. That is an we will call reason here the area in terms of number of gates. For some circuit, it will give the micrometer square also, micrometer square area. It will approximately equal into the number of gates only. So the number of gates required to construct the n-bit adder is 46 number of gates. Now we'll see the RTL schematic. Here by using this symbol, we can able to see the schematic of that particular RTL code. So by just clicking on that, it will generate the Rtl schematic of that particular structure. So here it's showing that page 1 of 2. So for that, in order to show the entire circuit schematic here, known schematic. So this is the entire structure. A7 down to 0. A7 down to 0, B7 down to 0 are two inputs, and S8 down to 0 is a final output. Like that, we can check the Rtl schematic. Now see the technology schematic file. So this is a technology schematic file for that circuit. Now we'll see the critical path, how much time it will take to travel from the input to the final output. This is the critical path from the A of 1 to the S of 8. So how much time it will take to travel from A of 1 to the S of 8? We need to see the command window. So it will take the 8.7 is in path time. So it will take from the arrival, the required time is in 10. The data arrival time is at 1.31. So from the input to the output, these many number of paths are available. A of 1, it will goes from the A of 1 to the Y, and IX37, IX189. These are the intermediate intermediate standard cell exist from the A of 1 to the S of 8. This much time it will take to arrive from the one path to the one stage to the next node. So it will take totally 1.31. The difference between the arrival time and the required arrival time and required time is a 8.69. This is a positive in the sense your constraint files, your constraints met the design. If it is a negative, means if the slack time is a negative in the sense it won't met the timing constraint. We can simply say that it will violate the uh, constraints rules. So for that we need to once again recheck the critical path, and we need to resolve the particular issue. So like this, we can synthesize any verilog code by using the Leonardo Spectrum. Like it will generate the area in terms of the micrometer square or number of gates, and also we can calculate the critical. It will also generate the critical path report. Now we need to see the how that particular netlist file exists look like. So for that, data will this is a netlist generated from that Leonardo Spectrum. So here see all the wiring, intermediate wires converted into the standard cell forms, that is an XR2, XR2, NAND02. All the whatever the Boolean equations we assign to the NP data, that totally converted into the XRN MUX21 like this standard cells only. This file we need to give it to the DFT in order to check the design for testability functionality. So after verifying the DFT, we need to insert a scan in order to perform that scan instruction, or otherwise we need to perform in order to perform the DFT, we need to apply this particular netlist file, and then we need to insert the scan chains. There we need to use the ATBGs in order to verify the testing. After that, we need to go. After that, it will go for the fabrication and layout generation, placement, routing, and then fabrication. So I hope you understood how to do that, how to do the synthesis for the verilog codes, any kind of verilog code. So this particular Leonardo Spectrum generates the Rtl schematic, technology schematic, and also critical path, and it will shows the how many number of gates required to design that particular circuit in terms of the area, in terms of it will generate in terms of number of gates or micrometers, or